this is where we stopped, okay? If you look back at your notes, you will see that we finished number 1, but we have not done the second problem yet. And if you look back at what you have written for number 1, you should see a net ionic equation that you used in number 1. Okay? Just to remind you, okay, you don't always need a net ionic equation. The only time you need that is if you're being asked to do something with an actual ion. Okay, that's what this says up here. If you're dealing with ions in the problem, or you're asked to solve for something with an ion, then you need a net ionic equation. Do you see anything about ions in number 2? No, neither do I. You still will need a balanced equation, but it doesn't have to be a net ionic equation. Okay? So the first step, and this is the very first thing we're going to do today, write out your reactants, predict your products, make sure it's balanced, and then do the math. Go! Multiple things going on in this problem. So let's talk about it. Okay? First things first, you need to come up with your balanced equation. And then I mentioned this last class. Get used to seeing this combination. You're going to see it all the time from now on. Sometimes, or very often, information will be given to you about an element or a compound where you're given a molarity and a volume. And when you always see that combination, what can you solve for? Moles. Okay? Now, if you'll notice, in this problem, both reactants have the same volume and the same molarity, so I only did this calculation one time. Okay? Now, if you have information about both reactants, what type of situation is this? A limiting reactant problem. Okay? And the question says, what mass of solid is formed? And you'll notice I did 2 separate calculations into grams of copper to hydroxide. How did I know to convert to this product and not that one? Yeah, Evan. Okay, NaCl would dissolve. It's a soluble compound. It will ionize. if something is insoluble, it remains a solid. Okay? And remember, the reason that this is insoluble, if you think back to your solubility rules, it says most hydroxide salts are insoluble, and then in parentheses there are some exceptions, and this is not one of them. Okay? Now, on our most recent test, we had a limiting reactant problem, and a lot of people missed it. Okay? And let me tell you what was the most common error. Most people did 2 separate calculations beautifully. You got the right numbers you were supposed to get, great. But the number one thing that I saw people doing incorrectly was, for some reason, adding these 2 answers together. You don't do that. What is the answer to this problem? Why is it 0.488? Okay. The smaller answer is your answer because it came from our limiting reactant. Okay. So that is the answer to the question. All right? 0.488 grams. Questions on that before we move on? Okay? We're going to do another one, similar. Let me just say, guys, this problem, we could have done this problem back in chapter 3. Is there any, we didn't need a net ionic. The only reason this problem is in chapter 4 is because we hadn't yet talked about molarity yet. That's the only reason that that's in this chapter. The rest of this is all stuff you've done before. So let's look at another problem. This is one of your problem set problems, okay, which we're going to do together. Okay, that takes the amount of work you have to do on your own down by 1. Okay, that also means next week when your problem set is due, there is no excuse for anyone getting a 0. You should all at least get a 1. Okay? So, let's look at it. The problem says, a 1.42 gram sample of a pure compound with the formula M2SO4. Do we all know that there is no element M? We do now. Okay. There is no element M. M stands for mystery element. Ooh. Spooky. Okay. So it says this compound is dissolved in water, treated with an excess of aqueous calcium chloride. So I'm just going to start underlining some things. Okay. This is my first reactant. Here is my second reactant, resulting in, oh, there's a typo, resulting in the precipitation of all the sulfate ions as calcium sulfate, first product. Okay? Now I actually want you to stop right there. Okay? I know I told you not to read any further. You're not actually going to be solving for anything with ions. I know the word ion is written there, but we're not going to be solving for anything related to an ion. So do I need a net ionic equation? No. I can just use the regular kind. Now I realize you don't know what M is, but you have enough information, stopping right here, that you can write a balanced equation. Do it. And then stop, and we'll continue. What's the other product? MCl. did you know that M had a +1 charge? Because you could have figured that out knowing the charge of sulfate is -2. Okay, let's balance it. Okay. Now, let's continue reading. The precipitate, and let's be more specific. We know the precipitate is calcium sulfate. Okay. Calcium sulfate was collected, dried, and found to have a mass of 1.36 grams. Determine the, I'm going to change this word, get the same number, but determine the molar mass of M and its identity. Okay, well, I'm going to give you a hint. Can you please tell me what are the units for a molar mass? Okay, grams per mole. Okay, meaning if you have some substance, element, compound, whatever, and you know its mass, and you know how many moles that is, you have these two values, if you divide them, it will give you that substance's molar mass that you would find on the periodic table. I want you to look at the information we have been given right here. Think stoichiometry. Look at the information given to us in the problem. Tell me, what could I do to start with this number? What could I do to solve for something that would allow me to get the molar mass of M, or maybe a compound that contains M? Throw out some ideas. Yep, okay, stop there. He's good, Good, okay. Okay. Let me say what he said. Let me make sure that everyone understands. Okay? We have a mass of calcium sulfate. If I do a two-step stoichiometry problem to turn mass of calcium sulfate into moles of this guy, look what else I have of that guy. I have the mass of that compound. I can solve for the moles of that compound. If I divide them, that'll give me the molar mass, like off the periodic table, of this entire compound. Now that's not the answer to the problem, but that's getting us there. So let's do that step first, and then we'll reevaluate and see what we need to do next. Okay, so that's not the final answer, but we're almost there. This is the mass off the periodic table of 2 M's, 1 S, and 4 O's. What do you suggest I do next? Subtract what? one S and 4 O's. Okay, fine. Is that the final answer? Why not? Because that's 2 M's. So we get, I'll move it over here. And what element is that? Most likely sodium. You're absolutely correct. Does sodium make sense charge-wise?
Yes.
Yes. Okay. Guys, I want you all to realize you could have done this problem back in chapter 3. There's nothing in this problem save one word that you would have understood back in chapter 3. We had not talked about a precipitate. That's the only thing. Everything else you could have done. Okay? Alright. Moving on. Alright. So folks, just to sort of recap what we have done so far. At the beginning of this chapter, we talked a lot of vocabulary about solution chemistry. We talked about how to make solutions, net ionic equations. We talked about precipitation. There's a next little small section on acid-base reactions. Okay? We are just going to skim the surface. When we get into third quarter, we're going to have a really intensive period of talking about acid-base chemistry. This is just skimming the surface. Okay? To remind you, back from chapter 2, you can always recognize an acid because acids, their formulas begin with hydrogen. And that's what acids do. They give away, they donate that hydrogen ion. Okay? Now I don't want you to be confused by this definition right here with the word proton. Look at this ion right here. Please tell me, how many protons does a hydrogen ion have? 1. How many neutrons does a hydrogen ion have? 0. How many electrons does a hydrogen ion have? 0. What? Plus 1 charge means it has lost that 1 electron that it did have. So guys, an H plus ion is nothing more than a proton. I know, I know, I know. Okay? So sometimes you will see acids defined like this. Okay? Folks, a base is the exact opposite. If an acid gives away a hydrogen ion, bases are things that accept hydrogen ions. And when you add an acid and a base together, I don't care what the products are. Okay? The products of an acid-base reaction are not always salt plus water. But anytime acid plus base are being put together, that is, by definition, a neutralization reaction. Here is an example. Okay? And I want you to look from this line down to the net ionic equation. It comes from this one. Okay? I realize I have not written out that middle step. But if you look from here to here, you can see that this compound is soluble, this one is soluble, this one is not. Let's just review a little bit. I know you don't have them memorized, and you probably don't have them in front of you either, but just try me. Can you tell me why this compound is soluble? It's a strong acid. Very good. How about that one? Okay, it's got an alkali metal in it. It's also a strong base. That's the more important reason. What about this guy? Alkali metal. It's got a halogen in it. Okay? ladies and gentlemen, water never, ever, never, ever, never, 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 ever splits up. Do I need to say it again? Ever. Okay. Now, no. Save yourself some time. This is a really good test-taking tip right here. If you come across a problem and you see that you're going to need a net ionic equation, if it's acid plus base and it's strong acid plus strong base, this will be your net ionic equation every single time. Save yourself the minutes that it would take you to write all this out, look down your solubility rules, break it up, break it up, break it up, don't break it up. Save yourself that time. Okay? Now, let's talk a little vocab. Right? When we go into the lab and we do a neutralization reaction, we give it a different name. We call it a titration. Some of you will have done a titration in your Chem 1 class. Some of you won't. We are definitely going to be doing this year. Okay? Can you tell me the name of this piece of glassware at the top? It's not a pipette. Burette.
Oh.
And it does not get a French pronunciation, burette. No. Okay, it's burette. Alright? When you're doing a titration, which means acid plus base, whichever one, and it doesn't matter, whichever one you have in the burette, whether it's the acid or the base, you call it the titrant. Okay? Titrant. Whichever one you have down in the flask is called the analyte. Okay? Again, doesn't matter if it's the acid or the base. And folks, the entire purpose of doing a titration is usually to reach what is called the equivalence point. So I want you to imagine that I've got the acid up here and the base down here. I will have reached the equivalence point when I've opened the valve here and let into the flask an amount of acid that is equal to the amount of base that was already in there. That's called the equivalence point. Okay? And some of these math problems that we're going to see, they will either say something like, maybe they'll be very direct and say this titration is at the equivalence point. But sometimes, usually they're a little more cryptic and they'll say things like, this amount of acid was required to neutralize this amount of base. They are telling you you're at this point. Now, why would that be something helpful? Because if you can find moles of one of these, you've got moles of the other one as well. For those of you that have done a titration, do you remember what the chemical is called that is responsible for it turning colors? Not a buffer, an indicator. Okay? We need a visual clue to tell us we've reached the equivalence point. And that's what that pink thing is, pink stuff. Okay? This is just another vocab word. End point means the point at which it changes color. And your titration is at an end. So, here's the deal. Folks, just because these are acid-base problems does not really make them any different than what we have been doing. The same rule still applies. Do you think I need a net ionic equation in this first one? How about in the second one?
Yes.
Yep. Okay. Same situation. Now I want to just address something real quick. For those of you that have printed out the PowerPoints, I made a change to this slide this morning. The only thing that's different, I changed the compound in number 1. I think it was calcium hydroxide. I changed it to lithium. I left the numbers all the same, but that has been changed. Okay? And here are your 2 hints, and then I'm going to stop talking. What does it mean if it says this amount of base requires this acid for neutralization? We're at the equivalence point. What do brackets mean? Molarity. You're being asked to solve for a molarity. Try these. So, ladies and gentlemen, just to wrap up number 1. Okay. Doing this allows me to get moles of the acid. Why can I make this? Why can I do that? Okay.
They're the same.
We're at the equivalence point. They're in a 1-to-1 ratio. I get the same number of moles. Divide, and I get my molarity. Okay. Try number 2. It's a little bit trickier. Alright, I'm just going to stop here for a second. Okay, this is not the end of the problem, but I want to just make sure some things are clear. Okay, first of all, this is the net ionic equation because it was strong acid plus strong base. Okay? Then, in the problem, I was given molarities and volumes, one for the acid and one for the base. Multiply them, you get moles of the acid, moles of the base. Why is this step necessary? We talked about this last class. Why do I have to do that? Why don't I tell you? Oh, Evan.
You have to figure out how many moles of the ions there are.
Right. Right. This given information, I've got to get it into units of something that is in my net ionic equation, which is the ions. And that's where that 2 comes in. Alright? Now, from this point, think about what you have. You have amounts of both of your reactants. What situation is this? Limiting reactant situation. Well, listen. We're being asked to figure something out about the excess reactant. Before I answer that question, can you tell me which one is the limiting reactant? How do you know that? Okay. Now I want you guys to be very, very careful with this one. What Alan said is correct. This is the limiting reactant. How did you know? Because there's less of it. Now, The only reason he can use that argument is because the reactants are in a 1-to-1 ratio. If they were not, if there was like a 3 coefficient and a 4 there, you can't just look at them like that. Usually what you have to do in a limiting reactant problem is turn each reactant into some amount of product and then figure it out. The only reason I don't have to do that in this problem is because everything's 1-to-1-to-1. Okay? So, let me write it down. Limiting, what's the opposite of limiting? Excess. So this is the one I care about. Here's the next question to you. You are asked, what is the concentration of hydroxide that is left over? That's not what this is. This is the amount of hydroxide I have at the beginning of the reaction. Tell me how to figure out how much hydroxide is consumed.